Hello everyone, I'm host Senyu from Shaanxi University. I'm very pleased to introduce our work titled Directional Label Diffusion Model for Learning from Noisy Labels. There are two main aspects to the background of our work: the prevalence of label noise and its negative impact. First, statistics show that label noise in real-world datasets ranges from 8% to 38.5%. For example, common classification datasets like Cvpr, Animal, 10N, and WebVision all contain label noise. Second, label noise often misleads model training and increases the risk of poor generalization. In supervised learning and complex real-world applications, making models robust to noisy labels is both critical and challenging. Traditional methods for learning with noisy labels include robust loss functions, regularization, sample weighting, robust architectures, and ensemble methods. Most of these approaches are limited to the discriminative paradigm. In contrast, our work is inspired by generative models, exploring how to generate corresponding labels from image features. Some previous studies have made initial attempts in this direction. For example, the LRA diffusion work uses diffusion models by treating labels as the diffusion target and image features as the conditioning input. However, these approaches lack interpretable noise information to help the model robustly generate accurate labels. We propose a new paradigm called Directional Label Diffusion, which decouples traditional label diffusion into two separate paths: directional diffusion and random diffusion. Directional diffusion is designed to provide additional noisy label information. For example, in the illustration shown, the true label of the image is car, but it can easily be mistaken for frog. So, we intentionally provide the noisy label frog as guidance, helping the model to focus on avoiding this incorrect direction during the subsequent label generation process. Meanwhile, random diffusion retains the standard diffusion mechanism, ensuring the model can recover clean labels from random Gaussian noise. During the forward diffusion process, we introduce a directional noise offset to the labels, establishing a new forward distribution. In the reverse process, we derive a new conditional posterior distribution and train two separate diffusion models to learn the decoupled diffusion paths. The optimization objective of the model can be simplified into the forms shown in equations 12 and 13. Specifically, besides minimizing the difference between the predicted noise and the random noise, we also aim to minimize the difference between the predicted directional offset and the actual directional offset. Unfortunately, in noisy training datasets, only noisy samples are available for training the diffusion model, and there is no prior noise information. To address this, we designed an efficient pre-correction strategy. The overall model architecture is illustrated in the figure on the right. By combining a frozen pre-trained feature extractor with a dual-view approach, we pre-correct the noisy labels before feeding them into the forward process. At the same time, we estimate the noise distribution to guide the reverse process. We first conducted experiments on a synthetic noisy dataset containing instance-dependent noise to validate the effectiveness of the DLD model. As shown by the cursor in the results, DLD achieves higher test accuracy compared to all state-of-the-art methods, especially when combined with the VIT model. We also evaluated the performance of our proposed pre-correction method and the full DLD architecture under various types and levels of noise. The results show that the pre-correction method is both fast and effective, while DLD further improves accuracy on this basis, demonstrating the value of the decoupled diffusion paradigm. We also conducted extensive comparative experiments on various real-world noisy datasets. The results show that our proposed method outperforms multiple state-of-the-art approaches, proving its practicality in real-world scenarios. Finally, the main contributions of this work are proposing a dual diffusion architecture for learning with noisy labels, designing a fast label pre-correction method, and refining feature conditioning. We focus on solving two key problems: how to address the learning with noisy labels problem from a generative perspective, and how to recover clean labels from features using explicit noise information. Thanks for your listening. If you have any questions, please contact me through this given email address.